Hey everyone, Bill Kinney here. I'm really excited to share with you some content that I posted just yesterday at my blog, infinityisreallybig.com. June 12th, 2019, I posted section 1.4 of my Visual Linear Algebra online textbook. The title of the section is Linear Transformations in Two Dimensions, and I think it's a really cool topic, and it's also foundational if you're going to understand all of linear algebra. Okay, it is kind of a long section, a lot of writing and a lot of visuals, both static pictures and animations like you see here. And as always, what I want to do in the video here to go with this section is I want to give you both a broad overview of the purposes of things and give you some subtle details about the content that you may not get from just reading it. As always, if you want to support me, I'm an Amazon associate, and I have links to some books that may be of interest in my blog. So if you click on the links to those books, if you are interested in them, that's one way to support me if you buy those. All right, so again, I don't want to read what I've written here to you. You can do that on your own. You can pause the video as I go through this and read it, or better, you can actually go to the site infinityisreallybig.com. But I will highlight some things to pay attention to. First thing to pay attention to is some terminology, and sometimes some confusing terminology. So let's get into that. I've already alluded to the idea of linear transformations in two dimensions before in my book. In the very first section, 1.1, Points, Coordinates, and Graphs in Two Dimensions, I talked about that linear transformations can transform, for example, rectangular coordinates into slanted coordinate systems. And I said that was part of a big purpose of linear algebra. This idea of a linear transformation is related to that. It's related to coordinate changes. Also, if you look in the exercises of that section, there's a system of linear equations that transforms rectangular coordinates into rotated coordinates, and that does define a linear transformation. We have talked about rotations before in section 1.3 as well, when we talked about visualizing the process of elimination there. Those rotations, however, were not about the origin, and that actually makes those rotations nonlinear. It's only rotations about the origin in two dimensions that are linear transformations. Before we get into linear transformations, we should review something you should already know from algebra or pre-calculus or calculus, and that is what is a linear function in those classes. It's a function of the form y equals f of x equals mx plus b, where m is the slope and b is the y-intercept. Its graph in rectangular coordinates is a straight line. It's a linear function in those classes. This actually presents a problem in linear algebra, however. In linear algebra, such a function would not be linear, would not be a linear transformation unless b is 0. Okay, so the presence of the plus b is a problem, so to speak, in linear algebra in terms of this new way we want to define a linear function or a linear transformation. That leads into this next section, which talks about some terminology and ways of visualizing things. When we use the word transformation in math, that is basically a synonym for function. However, it's kind of a special function that's got a geometric connotation to it. Okay, so we are going to think about things very geometrically here. But just realize transformation means function, and also when we visualize them as what I call here linear mappings or linear maps for short, that the word mapping or map in math is also a synonym for function. So there can be some confusion here. I'll tell you there's even another synonym for function that I don't bring up here. That's the word operator. We will bring that up in later sections. We want to view linear transformations in the plane in two dimensions in terms of what they do to sets of points. And in this particular post, I talk about what happens to a set of points that's in a parallelogram, and also another set of points that forms what's called the butterfly curve under various kinds of examples. You want to imagine you've got a starting picture that's a subset of the domain, which will be the plane, and it gets mapped or sent to, under the function, under the linear transformation, some other set of points. That's a subset of the codomain of the function. The domain and codomain are both the plane in this example, so they're the same thing. However, we are thinking of the domain sets as being mapped to the codomain. You'll see what I mean here as we get into the examples. That is the most important way to visualize linear transformations, but I also do want to talk about another way to visualize them as what are called linear vector fields, which take a given set of points in the plane and attach vectors to them. You'll see what I mean when we get there. That's going to be less important for us, but we will still talk about it in the book. It's important for the application of differential equations, which is very near and dear to my heart. All right, so again, we're going to explore through examples. Before we get into the examples, a little bit more notation. We are going to find it helpful to use this symbol that you see here, an R with a 2, like it's an exponent or something, as the symbol for the plane, okay, with rectangular coordinates is the way we usually think of it at least. The funny looking R stands for real numbers, and that's just emphasizing that the coordinates of the points are real numbers. The 2 represents the fact that it's two-dimensional, it is the plane, and our coordinates are ordered pairs. We're also going to use this arrow notation for a function whose domain is the thing on the left. The A is the domain, which will be the plane for our examples, and it maps points in its domain to its codomain, B, which will also be the plane for our examples. So the inputs are from A and the outputs are from B. That's going to be standard notation as well. Now let's get into our examples. The first example of many examples, again this is a long post, but again this content is really key, is a reflection about the horizontal x-axis. Define a transformation. Here I'm using the notation T, that's the name of our function, our transformation, that takes points in the plane, R2, and maps them to points also in the plane, R2. We're defining it geometrically initially. Take a point whose rectangular coordinates are x, y, and map it reflected across the horizontal x-axis. So if the point starts out above the horizontal x-axis, its y-coordinate is positive, it's going to get mapped to a point whose y-coordinate is negative below the horizontal x-axis. It's the reflection, so that point below is directly below that starting point, and it's the same distance from the horizontal x-axis as the starting point. This also means that if the point starts out below the horizontal x-axis, it gets mapped above it. Okay? If its second coordinate is initially negative, for the input, the output is going to have a second coordinate that is positive. If a point starts out on the axis, it's got a 0 second coordinate, it stays where it is. It gets mapped to itself. That's sometimes called a fixed point of the mapping. More notation here, including what is called, this is function notation here, t of xy equals x comma negative y. That's the formula for this function. You'll also see other authors and me use what is called maps to notation. X comma y gets mapped, sent to x comma negative y. More notation. Okay, these are all things that are worth talking about. It's not just done to fill up space here. Sometimes you want to give names to the output, just like functions in calculus. Y equals f of x. The input is x, the output is y. We give names to things. So we might want to do here with linear transformations. U comma v could be the name of the output point, okay? Equals t of x comma y. You could write the formulas for u and v as a system of linear equations. Linear equations, first powers of x and y, with no constants being added. U equals x, v equals negative y. How do you visualize the mapping? I already talked about that here. Here's a visual for it. I talked about it with my fingers and hands here before. That's one way to visualize the mapping, as a mapping of points. There's another way to visualize the mapping as a mapping of vectors. That's this picture right here. But remember, we've talked about the natural association between points and vectors before. Given a point in the plane with a rectangular coordinate system defined on it, you can naturally associate the point with a vector, a position vector for the point. Start an arrow at the origin and make it go out to the point. That's what you see here. We've got an arrow starting at the origin. The tip of the arrow is the point that we were talking about. It's getting reflected across the horizontal axis to a point or arrow that is its reflection across that horizontal axis. Here, also notice that I'm using vector notation. I'm using column vectors, as I usually will for vectors, instead of horizontal point notation, ordered pair notation. You should feel free to use either perspective. That's really important. Okay, we're going to have this natural association between points and vectors. You don't want to let it confuse you. Be able to go back and forth between these different perspectives. All right, we're about to get at the animations here now, but before we get into that, there's some terminology. By the way, the majority of the writing in this post occurs in what I'm showing you right now with the content before example 1, then in example 1, and some in example 2. After that point, it's mostly visual. So this is the majority of the hard stuff. Suppose we have a set of points, capital A, that's a subset of R2, which we're thinking of as being in the domain of T. It's often important to figure out the set of all outputs of A under T, under this mapping here. That's called the image of A under T, important terminology. It's defined by this equation that you see here. In this equation, I'm using what's called set builder notation. Okay, curly braces indicate set builder notation. I'm describing a set of points. In this case, as you look at this equation, T of A is the set of all points T of x comma y. Then the vertical line means such that x comma y is an element of A. It varies over A. This funny looking E symbol here means is an element of or is in. Okay? So that's something else to get used to if you've never seen that before. I actually am experienced in knowing that high schools don't seem to teach this as much as they used to. And now let's consider a particular example. A is this particular set, the set of all points x comma y, satisfying these inequalities. Now it's not clear what this set is, okay? I'm just describing it with some inequalities here. I say that with a little bit of algebra work, you will see that this is the parallelogram bounded by 4 lines, y equals 1/4 x, y equals 1/4 x plus 5 halves, y equals 3 halves x, and y equals 3 halves x minus 5. That takes some work to figure that out. I'm going to leave that to you. Okay, that's an exercise for you. But it is a parallelogram, and here's an animation showing how A is transformed into its image, T of A. In this animation, the parameter lambda that you see here that goes from 0 to 1 is just an animation parameter. It doesn't really have much meaning besides just telling you how far A has been transformed into its image T of A. That starting picture when lambda is 0 is A. It is the parallelogram that I described above. The ending picture when lambda is 1, right there, is T of A. Everything in between is just sort of a way to visualize the transformation as a reflection, and I think it's beautiful. It's a nice, beautiful way to visualize how A gets reflected across the horizontal x-axis, how A gets transformed into its image. Okay, a more interesting curve is something called the butterfly curve, which can be described with parametric equations. I'm not going to get into that, but here you see a beautiful butterfly in red that is the starting set A when lambda is 0. When lambda goes up to 1, it gets transformed into T of A, which is the upside down butterfly. The butterfly is getting reflected across the horizontal axis. What makes this reflection linear? Okay? Well, you can look at its formula and say, hey, the T of x comma y as a vector is another vector x negative y, or point if you prefer. And you could say, hey, the formula there, the x and the negative y, only involve first powers of x and y. So maybe that's the reason it's linear. But if you take that kind of naive view, there is a problem that if you added in constants here, like we will with an example later, it actually would turn out to be nonlinear in the new sense in linear algebra. Here is the more important related reason, related to the fact that we only had first powers of x and y. We want this equation to be true for linear functions or for linear transformations. Okay? T of an arbitrary input of the form SU plus TV, where U and V are arbitrary vectors and S and T are arbitrary numbers, scalars, must equal S times T of U plus T, little t times capital T of V. Okay? Kind of a strange equation if you're not used to this kind of thing, but this is the key linearity condition. Okay? This combination, SU plus TV, it's called a linear combination of the vectors U and V. All right, we're going to talk more about linear combinations a lot in later sections. So what we're saying is when you have a linear combination of u and v as inputs to t, the output is the same linear combination with the same numbers s and t of the images t of u and t of v. That's kind of a mouthful. All right, you may want to rewind it and hear me say that again. Okay. By the way, when you see just a plain r, that with no quote-unquote exponent, that just means the real line s and t are real numbers or scalars. To see why this is true, it's just a matter of using the definition of how to add vectors and how to multiply them by scalars, which I did talk about in section 1.2 on vectors. And use the formula for capital T, this formula right up here, okay? And here's the details. The key point is that this vector is the same as this vector in the end, okay? That means this equation right here is true for arbitrary u and v and for arbitrary s and t. Doesn't matter what they are, right? That's the key for linearity. Again, what makes that work is the first powers of x and y in the formula and the fact that there's no constants being added. In these two examples that you see here, especially look at example 2 here, I added a +1 in there. That actually makes it a nonlinear transformation. You will be able to find vectors u and v and scalars s and t where this inequality holds, okay? So that's another exercise for you. The first example here involves an x squared. That's also a nonlinear transformation, as you probably would guess before learning about this formula right here, okay? All right, we're on to example 2. Take a breath. Example 2 also has a fair amount of writing in it, but again, later, after example 2, the later examples don't have nearly so much writing, all right? It's mostly visuals, but it's worth trudging through this writing. The second example is a reflection about the line y equals x, okay? The 45-degree line through the origin. May be less clear what the formula should be. If you think carefully, I claim the formula is this. T of xy equals y comma x. We're swapping the x and the y around. That's its formula, or in maps 2 notation, you write it this way, or with vectors, you'd write it this way. Okay? These are all different ways of describing the same linear transformation. As a system of equations, you can write it this way, that you see here. Don't get confused by the fact that we've put the y first and the x second. We've swapped the coordinates. For the output, y ends up being the first coordinate of the point, of the output point, and x ends up being the second coordinate. Okay, that is okay to do. Here's a visual. Okay, here you can see the 45-degree line, this dashed green line. You've got the starting point xy that's above and to the left of that vertical, or that 45-degree green line. You reflect it across that line to another point. What happens to get the reflection? You draw the perpendicular, green as a perpendicular bisector of the line segment between these 2 points. The angle that you see here and here are going to be 90-degree angles. And you can certainly see for this particular example that I chose, it seems like you do swap the coordinates. The starting point, the input point, has coordinates -2, 5. The output point over here you can see has coordinates 5, -2. And that's what I say down here. Okay, so it's not a proof that that's the right formula, but it should make it seem reasonable. And if you think about lots of other examples, you'll see it seems reasonable. Once again, we talk about images of sets of points. I'm going to have the same parallelogram and the same butterfly curve in each example. So here you see the parallelogram getting reflected across that 45-degree line, y equals x. A is the red one, that's the starting parallelogram. T of A is the blue one, that's the image of A. So it's reflecting it in an upward direction here. Lambda is going back and forth. You want to think about what's happening as lambda increases to see the true nature of the linear transformation. Here's what happens with the butterfly curve. The red one is A, the blue one is B, or is T of A, is being reflected across that diagonal line. More writing here. What makes the reflection linear? Once again, it's this condition that needs to be true for arbitrary vectors u and v and for arbitrary scalars s and t. I'm not going to check that here like I did with the first example, but I do take the time to note a couple other things. This one equation is equivalent to 2 other equations being true. This first one that you see here just focuses on vector addition. The second one focuses on scalar multiplication. That could be proved that this one equation being true for arbitrary inputs is equivalent to these two equations being true. Sometimes it's easier to break it down that way. It's also worth remarking that we can take arbitrary linear combinations of vectors, of a finite number of vectors and a finite number of scalars, and get this equation to be true when you have linearity. Mathematical induction can be used to prove that. If you know about mathematical induction, you may want to do that proof. I will sometimes use sigma notation, summation notation. This last equation can also be written like you see here with the summations. Okay. These properties that I've been highlighting here have a name. They're sometimes called the operation preserving property of linear transformations. That's just something to be aware of. All right, we're going to go quicker now because we're just going to mostly focus on the pictures. Example 3 is another linear transformation. It's an expansion away from the origin. That's also called a dilation. We're going to map the point xy to another point that is twice as far from the origin and along the same ray from the origin. You got the origin, you're drawing a ray, which is just a directed line that goes on forever in one direction. So if you got a starting point, here is the origin. You'd want to take that starting point and make it twice as far from the origin along that same ray. That's what you see in this picture down here. And the formula is pretty natural to see that it should be what you see here, either in point form or vector form, or as a system of equations, what you see here. Just multiply the coordinates or components by 2. And that is the formula for this linear transformation. Here's what it does to the parallelogram A, which is in red. It gets transformed to a bigger parallelogram, twice as big, you might say, T of A in blue. Twice as big lengthwise, actually 4 times as big area-wise, okay? 2 squared being 4. Here's what happens to the butterfly curve. The original butterfly is in red. Its image, T of A, is in blue. Lambda, again, is just an animation parameter. You can take the time to check the linearity condition. Again, it works because the formula is linear, and there's no constants being added. Okay? No plus 1s or plus 7s or minus 4s in that formula. Example 4 is a rotation about the origin by 90 degrees in the counterclockwise direction. Map a point to another point or vector that is 90 degrees about the origin. And by the way, if you didn't notice, I am doing in these visuals both points and vectors. Its formula is a little less clear. It takes some work to figure out that its formula should be this. I'll leave that to you. It should make sense if you look at the picture. This point has coordinates 5, 2. That's the input point. It gets rotated to this point, which has coordinates -2, 5. Okay, and that would work in general, no matter where your starting point is. So you should take the time to think about some more examples of that. Here's what happens to the parallelogram. It gets rotated by 90 degrees. It's a rigid motion. Its area is staying constant. Here's what's happening to the butterfly curve. It's also getting rotated by 90 degrees about the origin. These are linear transformations. I am going to show you some nonlinear ones, though, so be aware of that. Example 5 is called a shear transformation. I'm not sure why it's called a shear transformation, but that is the common name given it. This one's a bit harder to describe. It's actually best initially described in terms of what it does to, say, a square whose base is on the horizontal axis and whose lower left corner is at the origin. It's going to sort of make it deform this way. That's what's going to happen. It's going to shear it. Again, I'm not sure the origin of that term. It's like if it were a building, it's causing it to become a slanted building. Okay, so you might wonder if it's related to slanted coordinates. It's going to map the vector 1, 0 to itself, that horizontal vector on the horizontal axis. It's going to get mapped to itself. And it's going to map the vertical vector 0, 1 to a slanted vector 1, 1. Okay? It's going to have a similar kind of effect below the axis, but the slanting is going to go the other direction. Turns out the formula for it is this that you see here, and as a system of equations as this. Here's what it's doing to an arbitrary vector xy that happens to be on the y-axis, so actually its x-coordinate is 0. It's getting mapped to this point, x plus y, comma y. If it's below the x-axis, it's getting mapped to this point, x plus y, comma y. You should try this with some examples. You can have an input point that's not on the vertical axis as well. Here's what it does to images of sets of points. It has sort of a pushing effect. With a parallelogram here, it's like the parallelogram is getting pushed to the right. This does actually preserve the area of the parallelogram, but it does not preserve distances of points in the parallelogram. Here's what's happening to the butterfly curve. Notice for points that are below the horizontal axis, they are getting pushed to the left instead of the right. This is the shear transformation, and it is linear. Here's an example that's nonlinear. I don't have visuals for this one because I think the visuals are pretty easy to imagine. It's a translation. What's a translation? It's just a shift. That's a rigid kind of geometric motion, just shifting points like a parallelogram, upward or downward or whatever. It's rigid. It's fairly simple, but it's actually nonlinear. If we take points and shift them to the right by 3 units and upward by 2 units, the formula for the mapping is this, which looks linear. You got first powers of x and y. But the +3 and +2 mess it up as far as this property goes. You will be able to find scalars s and t and vectors u and v where this inequality holds. In fact, I've got an example right here, okay? And the punchline is this vector is not the same as this vector. All right, so this is actually nonlinear because of that. Even though it's simple, okay? Simple doesn't necessarily mean linear. Even though its formula looks linear, okay? Right here. If I can highlight it, that's the problem. There we go. Okay, even though the formula looks linear. Okay, again, no pictures. This next one also has no pictures because it's easy to imagine. Rotation about a point that is not the origin. Some other point, like in my third section when I visualized elimination. This is actually a nonlinear transformation as well. What's a formula? What's an example we could consider? For example, suppose we want to rotate points by 90 degrees counterclockwise about the point 3,2. Well, this content that I have here is just a way of figuring out the formula for that. Essentially, I translate first to the origin, then rotate by 90 degrees, and then translate back to the original point. The formula ends up being this. And again, the +5 and the -y1 conspire to make this a nonlinear transformation. Okay, so rotation about points that are not the origin ends up being nonlinear according to this new definition of linear. Example 8, polar coordinates. A quote-unquote strongly nonlinear transformation where I'm not defining what strongly means. We did discuss polar coordinates in section 1.1. Essentially to contrast it with rectangular coordinates, but it's a common kind of application situation. Its conversion equations, x equals r cos theta and y equals r sin theta, define a transformation that you could write this way. This ends up being nonlinear though. You might say it's linear in r, but it's definitely nonlinear in theta. Cos theta and sin theta are definitely very nonlinear functions. In thinking about this transformation and visualizing, I'm about to show you a visual that's pretty cool here in a minute. It's important to realize that the R2 that's on the left in this symbolism here has rectangular coordinates that we are going to label with an R and a theta, which is different than what we did with polar coordinates back in section 1.1, where we used polar grid lines. That's not an obvious thing to do, but it is the best thing to do to visualize this transformation. So r and theta are going to be the rectangular coordinates of the input. X and y are going to be the rectangular coordinates of the output. What happens under this mapping? Here is our visual. So we're taking the butterfly curve. Notice capital A in red. When you see that picture, it's the butterfly curve, and the axes are labeled r and theta. Then as it gets transformed into its image T of A, the axes become labeled with x and y. Okay, that is the key way to visualize it. You do want to think about it that way. Why am I calling it a strongly nonlinear transformation? Well, you can see it looks like kind of a wild thing happening here. How A gets transformed into T of A. There's some sort of twisting going on. It's not really a rotation though, because the amount of twisting varies from point to point. Strongly nonlinear transformation, but interesting. Example 9, which is the final example, you'll be happy to know, goes back to a linear example. This is called projection onto the horizontal axis. It is linear, however it is different. It's degenerate in a certain way that I'll show you in a second here. Its formula is pretty simple. T of xy equals x comma x0. It's going to map or squash, project every point onto the horizontal x-axis, straight up or down. So this point here is starting above the x-axis. It gets mapped downward onto the x-axis. If the point were below the x-axis, it would get mapped upward onto the x-axis. It's called a projection because it's like you have light rays, say, coming straight down and straight up, and the blue dot or arrow is the shadow of the red dot or arrow when you've got these light rays either coming straight down or straight up toward the x-axis. That's why it's called a projection. Here's what happens to the parallelogram and butterfly curve all at once. Their images, T of A, become just lines, line segments. T of A, in both cases, you can't quite see it with the animation at the end here when lambda is 1, is a line segment. It's not quite showing you the lambda equals 1 case, which is unfortunate. But that's what ends up happening in the end. You get a line segment on the x-axis as the image. So it's degenerate. The picture, you no longer see a parallelogram or a butterfly curve at the end. That's why it's called degenerate. Here are some observations about the examples that I've actually mentioned to some degree already. Some linear transformations are rigid isometries. They preserve distances and areas. For example, rotations about the origins and reflections across lines through the origin, which I didn't mention yet, fall in this category. If you reflect across a line that's not through the origin, that actually ends up being nonlinear. There are some nonlinear transformations that are also rigid. Distances and areas are preserved. Translations, rotations about non-origin points, and reflections about lines that do not go through the origin fall in this category. Some linear transformations are not rigid. Expansions and projections do not preserve distances or areas, and shears do not preserve distances. I mentioned that already. For quote-unquote most linear transformations from the plane to itself, the origin is going to be the only point that gets mapped to the origin. No other points will get mapped to the origin. Projections are an example that's not that way. With our projection, the entire y-axis gets mapped onto the origin. That's equivalent to most linear transformations from R2 to itself being 1-to-1. And most linear transformations from the plane to itself, every point gets mapped, every point is the image of some other point. That's equivalent to most linear transformations being onto. Once again, the projection example is the only one that's not that way. The image of the entire plane is just the x-axis. Okay, there's still more content here. Hang on. The examples are basically done, but there's a couple more key things I want to talk about. Okay, so take another breath. Vector fields. The examples can be reimagined as vector fields, and I think this is even the coolest part. Okay, so hang with me here. Another way to visualize transformations is as what's called a vector field. Given a transformation, attach a vector as an arrow to the point xy. You might want to think of the output as being a column vector and the input as being a point. I do that with these examples, in fact. For examples 1 and 2, reflection across the horizontal axis and reflection across the 45-degree line, I'm writing the input as a point and the output as a vector. And we visualize it that way, including drawing a big dot at the origin when the output is the 0 vector, or the origin. This is the vector field for the reflection across the horizontal axis from example 1. This is the vector field for the reflection across the 45-degree line, y equals x. How do you draw these? How do you get a computer to draw them? For any input point, such as the point 2, 1, which would be right here, the output is a vector. For the first case, the output is the vector 2, negative 1. This arrow that you see right there, whose horizontal component is 2, it's rightward pointing, and whose vertical component is negative 1, it's downward pointing, is the vector with components 2, negative 1. That is the output of the vector field at the input. That is a point 2, 1. Try another point. Try the point negative 1, 3, this point right here. Plug it into this formula, you get negative 1, positive. Let's see, negative 1, 3. Okay, yeah. You get negative 1, negative 3. Okay, I was confused. This vector that you see here, this arrow that goes from here down to there, has component -1 for first component and -3 for second component. Points down and to the left. For the other one, the input 2, 1 has an output 1, 2. Swap the coordinates or components. This vector that's a little hard to see, that goes like this, has components 1, 2. Horizontal component 1, vertical component 2. It's rightward and upward pointing. Here are what the vector fields look like for examples 3 and 4. I'll let you maybe check a few points on your own. In fact, I've got points checked here for these two examples. This was the expansion or dilation. This was the rotation by 90 degrees around the origin. Here are the pictures for examples 5 and 6. This is the shear, and this is the translation. Notice this dot is no longer at the origin. That's another reason this is nonlinear, actually. All right, we're almost to the coolest part here. Okay, hang on. Here's the projection as a vector field. All the arrows are horizontal. And there's a bunch of dots on the y-axis. In fact, every point on the y-axis gets graphed with a dot, though you don't see that in the picture. Here's the almost to the coolest animation here. I talked about the relationship between the geometrically described mappings and these vector fields. Let's go back to the reflection across the line y equals x here, which we initially visualized this way. How do you connect this visual with the vector field? Here's the key animation. Okay. Notice the red vectors are what I call the identity vector field, x, y. You could, in a sense, think of those as being inputs. And the output vectors are the blue vectors. That's the vectors yx. That's the vector field yx here. Notice that I put a bunch of slanted lines here in pink, 45-degree lines. The initial red vectors, in every case, are getting reflected across that line, which is parallel to the y equals x line, to produce the output vectors, the blue vectors in that vector field. Okay, that final picture when lambda is 1 is the vector field we're after right now. Okay, and that's a way to connect the reflection picture with the vector field picture. Okay, that is the key way to do it. It is important. It's related to solutions of differential equations. In the subject of differential equations, you'd find solution curves, which are these curves that you see here, that follow that final vector field that was in blue right now. If you think about that final vector field in blue and the direction that the arrows are pointing now, you see these curves point in the same direction. And these are solutions to a certain system of differential equations related to that vector field. Okay? That's the content. I got exercises as usual. Here's the first 6 of them. And here's a couple more that are challenge exercises, and I forgot to label this one with the number 2. I guess I'll do that after making this video. Thanks for watching.